So now we are going to show you how to design a poor man's inverter, simple poor man's inverter. Its capacity is 100 watts. So we are actually watching ICC Cricket World Cup 2015. It's India versus Bangladesh. We love to watch cricket. Okay, leave it. So this is a very simple inverter circuit. It's easily portable and it costs only 120 rupees, which is very cheap. Even a poor man can afford to buy this. So with this inverter circuit, we can drive 3 CFL bulbs and a ceiling fan, which are the basic needs for a person. Definitely a person requires a fan and a light, but we can drive 3 lights and a fan. So you can see the output across the transformer using a multimeter. You can get 230 to 240 volts of an output, which is equals to the mains output. And this is a battery with which we provide the input supply to the circuit, to this inverter circuit. And this circuit converts the entire DC input 12 volts. We are giving 12 volts DC input, and the 12 volts DC input is converted into the 12 volts AC by this circuit, and this AC is given to the transformer, and the transformer step ups the 12 volts AC into 230 volts AC. So you can see the output across this multimeter. So if you see this, the multimeter is in a range of, you can see up to 750 volts. It's put in a 750 volts range. You can see up to 240 volts output. So now we are going to give the input. So from the transformer output, these are the 2 output pins of a transformer, and from the transformer they are given to the circuit. This is a plug board, and we inserted 3 CFL bulbs and a fan. So you can drive all of these things. So give the inputs. Now you can see this. So he is giving the input. Now you can see drawing all of these things. Yeah. If you see 3 CFL bulbs and 1 fan can be run with this small circuit. A very small circuit and very low cost circuit. So now I am going to tell you how to prepare this. This is a very simple to design, and we are also going to deal with what are the problems you face while designing with this inverter circuit, and what are the do's and what are the don'ts you have to do. Output voltage across the transformer is 232 volts, 230 volts. The multimeter is showing 230 volts. So now we are going to show you how to design it. Let's go into the design. How to design this, what are the problems we are going to face. So now I am going to tell you how to prepare this circuit, this inverter circuit, poor man's inverter. So it's a 100 watt capacity. So what is the basic principle of an inverter? Inverter is nothing but which converts DC power to AC power. It takes 12 volts DC input and converts to 230 volts AC output. So what are the basic necessities of an inverter? An inverter requires a battery, a circuit, a transformer. So firstly, battery. What is the need of battery? Battery is required to provide input supply to the circuit. And what type of battery you have to use? You can use a car battery or auto battery or any other battery which capacity is about 20 Ah. So Ah refers to the battery capacity. So you can use a 30 Ah battery, 40 Ah, 70 Ah, 120 Ah and anything else. So but it should be definitely greater than 20 Ah. So you may arise a question, why should you use a 20 Ah battery? Why can't we use less than that? So firstly, what is Ah? Ah stands for ampere hour. So you all familiar with the formula power equal to voltage into current, P equal to V into I. So we are designing a 100 watt inverter. So the value of P is 100 watts and V is the input voltage, it's 12 volts. And the current is equal to P by V from this formula. So it is 100 by 12, it is 8.3 amps per hour. It means our circuit draws 8.3 amps of current for 1 hour. But here there is a small technical problem with any inverter. Even with the inverters available in the market. Generally the inverter draws high startup current when they are immediately turned on. So with this inverter, the inverter draws a startup current of 10 amps per hour. So but the battery capacity is only 8.3 amps per hour. If you take the battery capacity is only 8.3 amps per hour, then the inverter cannot drive with the battery. So you have to use a battery. Definitely its capacity should be 10 amps, greater than 10 amps per hour, but the usually available batteries in the markets are about 20 Ah. So you have to use them. So let's go into the circuit design. If you see this is the circuit. Here it's a battery, and this is a diode, and this is an IC CD4047, and this is the circuit. So you can clearly get this circuit in the link below. You can download the circuit from the link below. So what are the components basically required in this circuit? It's IC CD4047, one and two resistors. I mean a resistor and two other resistors. So these are the components required for a circuit. So what are the main aim of this IC CD4047? So it is required to generate a square wave output. So what is the need to generate a square wave output? It is impossible to generate. I mean it's highly difficult to generate a sinusoidal output which we generally get from the mains. So generally the most of the inverters are run by using a square wave output. This CD4047 generates a square wave output. If you see this, here there is a C and R. This is a capacitor and a resistor. So these two are used to set up a frequency of 50 to 60 Hz. Generally you all are familiar with the concept that the output from the mains runs at a 60 Hz frequency. These C and R are required to provide that 60 Hz frequency. So how to calculate the frequency? With the CD4047 IC, this is a formula for calculation of frequency. F equal to 1 by 4.4 RC. So the resistor we are used here is 19 kilo ohms resistor, and the capacitor used is 0.22 microfarad capacitor. The capacitor used here is a 0.22 microfarad capacitor. So with this formula you can get a frequency of 54.37 Hz. That is almost equals to 50 to 60. It's in between 50 to 60. So the device can, generally the household device can run with these frequency range. So here the resistors R1 and R2 in this circuit. So the R1 and R2 resistors are connected from 10th pin and 11th pin of the IC CD4047, because these resistors make certain voltage to drop in them, so that you can protect the MOSFETs here. So there will be a slight voltage drop in these resistors so that you can protect the MOSFETs. So if you see this 10th pin and 11th pin of the IC CD4047, at 10th pin you can get a square wave, and even at the 11th pin you can get a square wave, but these two are opposite in polarities. It means at the 10th pin, if the wave starts with positive spike, at 11th pin it starts from a negative spike. One thing, a square wave contains a AC component plus DC component. So whenever you see the output in a multimeter, you can see the output across 10th pin and 11th pin as only 6 volts of AC. You don't think that we have given 12 volts of input DC, but we are getting only 6 volts AC. The rest of the 6 volts it's stored as a DC. So if you see the output across 10th pin and 11th pin, it shows 6 volts AC and 6 volts DC. Now I'm going to show you how it's going to be. So give the input. So now if you see in the multimeter, so I'm putting a 20 volts range. So now we are checking the output across the 10th pin and 11th pin. Now it's across 10th pin. You can see 6.23 volts. It's an AC voltage, and the rest of the component is, you can see, as a DC voltage. Now I'm turning it into a DC voltage. So you can see the rest 5.67. The entire addition of, it's turned off. Yeah. So it's a DC component and it's an AC component. Since square wave is a combination of DC plus AC, so this is what happening. 6 plus 5, it's almost 11 and 12. Okay. So far we covered the use of the C and R. So I'm just reviewing this. So C and R are used to set the frequency to 50 Hz, and these R1 and R2 resistors are used to make certain voltage drop in them, so that the MOSFETs doesn't get damaged. And now let's go into the matter. What is the use of this capacitor C1? This C1 is nothing but a 1000 microfarad by 16 or 25 volts capacitor. You can use anything. So this capacitor is used to smooth the output waveform. What are the output square wave we are getting? This capacitor used to smooth the waveform, and also it acts as a reservoir of charge. I mean, if you take the input supply, if you remove the input supply from the battery, then the inverter can work for some time, some fraction of seconds. I will show you in the experiment. So now I am going to show you experimentally how the 1000 microfarad capacitor, this is the 1000 microfarad capacitor in the circuit. You see, this is a very big, and it's a 1000 microfarad capacitor. So this acts as a reservoir. So give the input connection. Now I am going to prove you. So it's generally what the normal connections, we are just giving the input. So if you see this, we have given the battery input and a transformer input. So now we are removing the battery connection. This is a battery connection, battery positive. Now we are removing the battery positive, and the inverter keeps on working for a certain time. You can see that. So remove the battery input. So you can see the inverter turns on automatically after certain time, because this acts as a reservoir. You can see the bulbs are glowing less. So now they will be turn off automatically after certain time. So we also covered the use of this C1, and now let's go. Let's deal with the MOSFETs. So how the MOSFETs work, and what about the MOSFETs? So generally a MOSFET contains a gate, drain and source. These are the 3 pins of MOSFETs. So what are the MOSFETs you have to use in the inverter circuit? So this is the MOSFET, and now I am showing the MOSFET IRF 3205. So this is a gate pin, this is a drain pin, and this is a source pin. So every MOSFET contains certain tolerance rating. So IRF 3205 is tolerable up to 115 watts, IRF Z44 80 watts, 540N for 150, and P55NF06 for 60 watts. Generally we prefer this type of MOSFET because its rating is very high. You can use any of this for our inverter, because our inverter is only 100 watts. So the purpose of the MOSFET is for switching purpose. I mean, if you see this, if you consider the entire MOSFET setup in the upper part as Q1 and in the lower part as Q2, whenever the Q1 is on, Q2 turns off. If Q2 is on and Q1 turns off, it's a switching purpose. So what is the need of switching? To produce an AC wave across the transformer output, switching is definitely necessary. So one more important thing I forgot to tell you, you can use this upper part as a drain. This is a drain of a MOSFET, and you can use this entire steel body across this upper part as also a drain. So you may get a doubt, there are transistors, we can also use transistor for switching purpose. No, but the transistors are very low capacity transistor. I mean, they could not tolerate for inverter, so they are not preferred generally during the construction of an inverter. Transistors are not capable, they are not high as efficient as an MOSFET. So if you see here, generally we use 2 MOSFETs. So you may get a doubt, why should we use 2 MOSFETs? Why can't we use only one single MOSFET? So we use 2 MOSFETs because by connecting the MOSFETs in parallel, this is a parallel connection, by connecting the MOSFETs in 2 parallelly, they can share the current, so that whenever you place a load, the MOSFETs doesn't get any strain. I mean, the load effect can't show, so that if you increase the load, the MOSFET doesn't damage. If by placing 2 MOSFETs, you can increase the wattage of an inverter by increasing the number of MOSFETs. You can connect 3 MOSFETs in parallel or else 4 MOSFETs in parallel. By that you can increase the wattage of an inverter. So one more important thing about the MOSFETs is, in the circuit you have to use all our similar type of MOSFETs. I mean, if you use an IRF 540N MOSFET here, if you use some other MOSFET, for example IRF Z44, there will be chances of different switching, so that you cannot get an exact output or else a distorted output. So if you want to use any MOSFETs in the circuit, you have to use all the similar type of MOSFETs. Okay, now let's go into the, we have dealt about this, and now let's go into the transformer. So transformer, what type of transformer you have to prefer? Generally center type of transformer, step up transformers are preferred for construction of inverters. So for the first time, when we are designing this inverter, without any idea we purchased a transformer. We thought it's working better, but it's a useless transformer. So be careful while purchasing a transformer. So don't just ask to give us a transformer. Ask for the rating of a transformer. So whether you want a 100 watt transformer, 200 watts or 300 watts, 500, whatever it may be. It's a normal step up transformer. center tapped step up transformer. So be careful while purchasing a transformer. So you can use these kind of transformer. This is a transformer used in UPS. It's a 600. This capacity is 600 VA, and you can also use that type of transformer, and that's capacity is 500 watts transformer. Yeah. So generally the rating of a center tapped transformer will be like this. Primary side rating, it may be 12012 or 909. What is this meaning? 12012 means 12 volts AC input, and 0, and this is also 12 volts AC input. So at the secondary side you can get 240 volts, 220 volts, 180 volts. You will have 3 slots like this. So this is a transformer. Yeah, you can have the slots like this. This is a negative, this is a neutral pin. Across one pin you can get a 240 volts, and at the other pin you can get 220 volts, and at the other pin you can get 180 volts, and sometimes some transformer have an extra pin, there you can get 100 to 120 volts. So the important thing about transformers is, while designing an inverter you have to put only 70% of load on the transformer, because generally transformers are not ideal. They have certain loss in them. For example, if your inverter transformer is 100 watts capacity, you have to put only 70% of load. That means you have to use up to 70 watts. You can put up to 70 watts of load. So for example, if it is a 500 watt inverter transformer, you have to put only 350 watt load on them. So one more important thing here is, when you are running a ceiling fan on an inverter, it makes a little sound. That's because the output generated with the inverter is a square wave output. So the sound is because if you run the same fan with the mains, which generally comes to your home, the mains output is a sinusoidal wave output. So the fan doesn't make any sound. But if you connect the same fan to this inverter, to any inverter, it makes a bit of sound. That's because it's running in a square wave. So we have also discussed about the transformer. So now let's discuss with the other parts remaining in the circuit. So additional protection to the circuit. How can you protect the inverter circuit? So if you see here, we use the normal PN junction diode. So it is used to protect the circuit. By placing the PN junction diode as shown in the circuit, you can protect the circuit from damage or from excess voltage. So if you see the battery, here we place the capacitor. This is not necessary. You can remove this capacitor. So if you see this, we connected a Zener diode across this MOSFET. It's between drain and source. Why we place a Zener diode here is, Zener diodes protect the MOSFETs from excess voltage. Sometimes there is a chance of getting excess voltage across the MOSFETs. So at that time you can protect the MOSFETs by using the Zener diode. Zener diode grounds the excess voltage here. So we use the Zener diode. You can use one Zener diode. No need of putting every Zener diode to every MOSFET. One Zener diode across the two MOSFETs is just necessary, and it's sufficient. Now I'm going to tell you what are the problems we faced while designing an inverter. So first we tried with the 555 timer, because 555 timer can generate a pulse waveform, that is a square wave output. But what's the problem with the 555 timer circuit is, this is a 555 timer circuit. So it cannot give a better results compared to CD4047. It cannot step up the voltage. You may get the 230 volts output with across the transformer, but what the problem we faced is, we are not getting the required current to drive all these equipments, 3 bulbs and a fan. So it's not preferred. So it's better to use CD4047. The next problem we faced while designing inverter is a little bit of wrong connections. If we give even a small misconnection, small wrong connection, the ICs are getting damaged. We lost many ICs, nearly hundreds of ICs we lost with small mistakes. What's the main problem? If you lost the IC, if the IC is damaged, the MOSFETs gets heated. MOSFETs gets excess heated. To protect the MOSFET we use heat sinks, but sometimes even with the excess of heat, the MOSFETs will be completely destroyed. So at that time, if you hold the MOSFETs directly, you will definitely get your skin burned. So it's better to avoid the contact with the MOSFET when the IC is damaged. So That's all. Now I'm going to tell you how to check the MOSFET whether it's damaged or not. Okay. Now I'm going to tell you how to verify a MOSFET whether it is working or not, whether it is damaged or not. Due to the excess heat, sometimes the MOSFETs may damage. So at that time, you can check the MOSFET using a multimeter. You have to put the multimeter in the buzzer mode. So this is actually in a voltage mode. Now I'm putting this in a buzzer mode. So this is a buzzer mode. So I'm verifying this MOSFET. So you have to place a drain. You have to check whether the gate and drain junction and drain and source junction is shorted or not. If they are shorted, then MOSFET makes sound. If they are not, then MOSFET shows, then the reading will be shown in the. So if it's a working MOSFET, then then multimeter shows certain value. So here I am verifying IRF Z44N MOSFET. It's failed. It's spoiled MOSFET. Sorry for the disturbance. So it's not working. This MOSFET is not working. So this is so I am connecting the drain. So you can use the upper part as a drain. So if drain are shorted, it shows certain sound. But what you have to check is whether the gate and the drain junction and drain and the source junction are shorted or not. So if you see here, this is a gate junction, gate and drain junctions. So it's making sound. The buzzer is making the sound. It means the junction is shorted. So this MOSFET is damaged. So now I am checking the drain and the source junction. Yes, even it's making a sound. It's damaged. If any one of the junction is also broken, then the MOSFET is damaged. So now I am going to show you a working MOSFET. So this is IRF3205 MOSFET. So I am given the drain. I have put the drain. So if you see this, you are not getting any sound. Sorry, I mentioned that it shows certain value. Actually multimeter doesn't show any value. You can check whether it is making sound or not. Here you are not getting any sound across the gate and the drain junction, and similarly across the drain and the source junction also you are not getting the sound. If you see it again with this damaged MOSFET IRF Z44N, it can make the sound. See, the drain and the gate junction is making the sound, and drain and the source junction is also making the sound. In this way you can check the MOSFET. So one more important thing I want to tell you is, don't do this circuit on a breadboard. Better you use a PCB board, because what the problems you face with the breadboard is, when due to the excess voltage the breadboard gets damaged and the side pins will be shorted. So that you cannot get an exact output across the breadboard on a breadboard. So this is when the MOSFET is overheated. This is the problem we faced. These 3 pins are shorted, and this is one more problem we faced. And due to the excess heat generated in the circuit, in the inverter circuit, the entire breadboard is damaged. You can see the holes, big holes. So sometimes the IC also gets excessively heated on the breadboard. So if you see this here, due to the placing of an IC, it's damaged. I mean, it's spring. The breadboard is spring. The breadboard cannot tolerate heat because it's made of plastic. So it's better to use a PCB board. So PCB board can tolerate heat. So sorry, I forgot a most important point. We tried to create inverter using this kind of batteries as an input. So you should not use these kind of 9 volts batteries as an input, or else you can't use these kind of batteries because their capacity is only 7.2 Ah. We need about 10 Ah capacity. So that's all. So one more important point I want to reveal you is be careful with the transformer, because the transformer can generate 230 volts output. If you are careless, you have to face the shocks. If you see that the transformer is not making any sound, it's not connected. Now we are giving the connections. So we are giving the connections. You can hear the sound in the transformer. Connect fastly, man. Yes. You can hear the sound from the transformer. So if you are careless, you may get the shocks. Even we face many shocks due to the loose connections and whatever it may be. Be careful with the transformer. So for more details, you can see the below link. So we will place we have written extra details in these papers. We'll put them in our link, so you can.
What is 60 watts?
Thanks
So
for watching.
70 into 12 by 60. It's 14 hours. The backup hours is 14 hours. With this inverter, with this battery, you can run the inverter for 14 hours. By using different batteries, a battery with different AH, there will be a difference in the hours of running the inverter. So I want to tell you two important points. First thing is how many hours you can use this inverter. That depends on your battery capacity. So we are using a 70 Ah battery. So this is a formula to calculate the backup hours of an inverter. Backup hours equal to battery capacity into input voltage by total load wattage. So we are using a 70 Ah Emeron battery, and we are providing 12 volts input. The battery is providing 12 volts input, and we put a 60 watts load. So the total backup hours is 70 into 12 by 60. It's 14 hours. It's the backup hours, number of backup hours. So the backup hours differ from battery to battery. If you are using a 20 Ah battery, the backup hours may be different. It may be some other thing. And one more important point I want to reveal is about the drains connection with the heat sinks. If you see the circuit here, the two MOSFETs are connected using a heat sinks. Now the entire heat sink can be acted as a drain. This is a most important point. Thank you. I promise you definitely get this. It works. Thanks for watching. Hi guys, a small correction. We mentioned you initially that our inverter capacity is only 100 watts, but with our recent test we come to know that it's capable up to 150 watts. So how did we confirm? So if you see this fan, it's a Sydney company fan. Its wattage is 110 watts. So if you see here, its wattage is 110 watts. So you can see here its wattage is 110 watts. Now I'm going to run this 110 watt fan with our inverter. So if you see the transformer, this is the output of a transformer. It is connected to the plug board. Now I'm connecting our fan to the plug board. Let's see how the fan works. Okay. Initially the fan is in off state. Now I'm connecting the fan to our inverter. So I am giving connections to the battery. Yeah, the current in the plug board is on. You can see the power running, and now I am turning on the fan. Let's see how it works. So you can see the fan is running as it was connected to the mains. How the fan works in the mains, in the same way it is running with our inverter circuit. So our inverter is capable above 100 watts. Now I am going to connect the tube light even. I am turning on the fan. I am turning off the fan. We have just seen that our inverter is able to run 110 watts fan. So now I am going to test the inverter with a tube light and a fan, which are the basic necessities. Nowadays nobody are using the bulbs. So most of the people are using tube lights. So now we are going to run this tube light of 40 to 50 watts capacity and a fan of 40 to 50 watt capacity, totally 100 watts. Now let's see how they run with our inverter circuit. So if you see this, we have already connected the tube light to our inverter. This is the output from the transformer. It is connected to the plug board. So now let's see how the tube light runs first. I am giving the input connections. Yeah, now I am turning on the plug board. Yeah, you can see the tube light is glowing. So now I am connecting the fan. Let's see how the fan is going to run. I am giving the connections of fan to the plug board. Yeah, both are running. But what's a small problem is its brightness is decreased a very little extent. Now I am removing the fan, its brightness increases. So it's not a big deal. It's a very little change in the brightness. So why I want to tell you this is initially we tried to glow this tube light and fan. We tried to glow the tube light and run the fan, but we could not make it. Initially the tube light is just blinking, but it's not glowing. But now why it is able to glow? Because initially we use these kind of wires as to connect all these wires. Initially we used instead of this 1.5 mm wire, 1.5 square mm wire. So this is a very small wire and it's a single lead wire. So initially we use these kind of wires in the inverter, these kind of wires and this very small wires, this kind of wire. It's a multi-lead wire, it's a single lead wire. So yeah, this is a single lead wire and this is a multi-lead wire. Initially we use these kind of wires, so we didn't get a proper output. So but now if you see this, we completely replace the entire inverter with the multi-lead wires and they are 1.5 square mm. You can get a better output if you use 2 square mm wires. Yeah. So that's why initially we could not glow a tube light with these kind of wires. So, and one more important thing, and what the problem we faced is due to the loose connections. We didn't get the proper output because of the loose connections in the circuit. It's better if you use these kind of clips, so that clips can hold the circuit very firm. They can hold the inputs very firmly. So avoid the loose connection in the circuit. Make the circuit very perfect. Give the proper connection, so you can definitely get a better output. And one more thing, what's happened if you use these kind of small wires? If you use small wires, I mean, I've shown you before just now. Where are the wires? I mean, these kind of single lead wires. Yeah, these kind of single lead wires. What's problem with these wires is battery generates high heat. So why couldn't we get proper output with these kind of wires is, if you see this, their thickness is, this blue wire thickness is very less compared to the red wire thickness. This cannot tolerate the heat, and moreover this is a single lead wire. It's soldered. So if you see this side, this is a single lead wire. They could not tolerate heat coming from the battery, and the wires also gets overheated. So we could not get proper output. If you use a multi-lead wire and 1.5 square mm thickness wire, so you can get better output. You can get very best output when you use 2 square mm wires, which are generally used for household wiring purpose. And that's all. Thank you. Thanks for watching. Guys, one more problem we faced is initially before trying the experiment using the hardware, we started by using a software. We use 3 kind of software: Proteus, Simulink and MATLAB. We tried to put our circuit in the software, and we just want to find the output. What's the output waveform we are getting? But we could not get the better results using software. So what we suggest is, it's better you go with the hardware. It's waste of time using the software. Better you design a circuit and put it on a hardware, so that you can get better results. Thank you. Thanks for watching. You will definitely get the output, I guarantee.